Today I wanted to tell you about Jellyfish, which is a multimedia server powered by Membrane Phoenix, which me and my colleagues have been working on since the beginning of this year at Software Mention. But before I start, let me introduce myself. My name is Łukasz. I work mostly on multimedia streaming and WebRTC, all of that in Elixir, at Software Mention in Kraków, Poland. You can find me on GitHub and on Twitter. So what's the agenda for the talk? I want to give you a little introduction to the concept of media server and some of the most common and relevant, in our case, media protocols and standards. Then I'm going to do a little overview and tell you about basic concepts and building blocks of Jellyfish. Then we're going to look at some examples and scenarios that you can achieve with Jellyfish, and there's going to be a little demo. And at the end, we're going to take a look under the hood of Jellyfish. So let's start with the concept of media server. So basically, media server is a piece of software that you run in your backend that receives some media via the network and then sends the media somewhere else, as simple as it gets. If you ever worked with WebRTC, you might have heard the abbreviation SFU, which stands for Selective Forwarding Unit. And the name is quite self-explanatory. It selectively forwards some media traffic somewhere else. Okay, so you might be asking, well, solutions like that exist on the market. It's not a new invention, so why are we building this thing? And before I answer this question, I want you to get to know some of the most common streaming protocols used nowadays. And the first one of them is WebRTC, which is a protocol, or rather standard, designed in the last decade for real-time communication. It was designed for peer-to-peer, but now it's commonly used with SFUs, so the media server. You might have guessed that the Jellyfish is also an SFU. It's based on RTP, which is a streaming protocol. It's characterized by very low latency, often sub 100 milliseconds, and can handle real-life network issues like congestion or simply bad network. It's used in video conferencing. All of the big players like Google Meet, Microsoft Teams, WebEx, Zoom, all of them uses the WebRTC. And what's very important, it's implemented in most of the browsers. So you have your JavaScript API for WebRTC, and you can very simply use it when developing an app for a browser. And this is an example scenario that you can achieve with WebRTC. So you have 4 instances of browser in this case. Let's say it's Chrome, and they can connect to each other peer-to-peer using the WebRTC APIs. And unfortunately, this doesn't scale very well because you have to do the upload by IP unicast to every one of the other peers in, for instance, a video conferencing meeting. So most of the big solutions like Google Meet use the SFU, the media server, that forwards the traffic somewhere else. The other thing on the other side of the spectrum is Apple's HLS, which is a broadcasting protocol. And it's used mostly in video on demand and live streaming solutions. For instance, Twitch uses HLS to stream. It uses HTTP, which means very widespread support. And it basically works as follows. You have your media, for instance, a video track. It is packed into a container very similar to your typical MP4. And it is sliced into segments, and each of the slices is then sent somewhere using the HTTP. And this is how you can use it. You have your server and some media on the server, for instance, maybe a live stream or some video, like a movie on Netflix, video on demand. And it is served via HTTP to all the clients. And because of the HTTP, it's scaled very easily, thanks to use of, for instance, CDNs. And the third protocol that I want to mention, and the last one, is not as widely used, but important in our case, is the RTSP, which is a very simple protocol based on RTP that adds some control over the multimedia playback. And it's suitable for streaming and broadcasting. Nowadays, mostly used by IP cameras. So if you have an IP camera that uses RTSP to send the media somewhere. And I'm talking, this is the example scenario you can achieve with RTSP. I'm talking about these 3 because these are exactly the protocols that Jellyfish supports at the moment. So while other solutions usually focus on one thing, like WebRTC, we tried to make an extensible solution that can bridge different types of protocols and somehow for interoperation between them. So for instance, you could create a video conferencing solution, but also want to stream the meeting somewhere via the HLS to a broader audience, for instance. And I'm going to show you the examples, the scenarios. But before that, I wanted to tell you about the journey that we took to get to the Jellyfish. So obviously we have the Elixir and Membrane. Membrane is a framework for Elixir for creating multimedia pipelines. And we needed to create real-time communication solutions with the WebRTC that I mentioned before. So we've made the Elixir library, which is called Membrane RTC Engine. But obviously, as a library, it has its own limitations. You have to use it with Elixir, which is unfortunately not everybody's choice. And you have to implement some things every time you use the library. For instance, the signaling, which is some metadata exchange between the client and WebRTC server, which is required for WebRTC to work. So we used Phoenix to wrap the Membrane RTC engine and created the Jellyfish, which is a standalone server. All right, so now I'm gonna talk about the building blocks and concepts that we use in Jellyfish, which are rooms, peers, and components. Rooms are basically containers, isolated spaces that can contain other types of elements, which are peers and components. You can think of a room as, for instance, a meeting in your video conferencing solution. I'll be bringing up the video conferencing solution very often in this talk, so you can think of it as something like Google Meet, let's say. And then we have the peers and components. Peers are basically instances that have some client connected to it. So for instance, the user, the participant in your video conferencing meeting. On the other hand, components are solely server-based entities. And here's some examples. So the only type of peer that we currently support is the WebRTC peer. And in the context of video conferencing solution, your app would look something like this. You have your backend, your frontend, and some client wants to join the meeting. He sends a request to your backend. I want to join the meeting. Your backend takes care of creating the WebRTC peer using the Jellyfish API that I'm going to discuss in a bit, and gets the peer token in return. Then your client can use the peer token to open the signaling connection between Jellyfish and your client. The signaling is necessary for WebRTC to work because there needs to be some metadata exchange between the client and the server. And after the metadata is exchanged, the actual media can start to flow. And this is the code from our SDKs. In this case, this is Elixir SDK, obviously. And that allows you to add the peer to your room. Obviously, this is a bit out of context, but I'm going to show more the fuller example later on. So you create your peer with the call to add peer function that takes client, which is a struct that aggregates some information required to make the request. You have your room ID, which is generated by Jellyfish, and then you add your peer, which is, in this case, WebRTC peer. You get your peer token. It has to be sent to the client somehow. We don't really care how. And then in your client, in this case, this is JavaScript, so maybe a browser, use the token to create a Jellyfish client instance, and then use the connect method to establish the signaling connection. And then you can use the usual WebRTC APIs to send your media. That was the peer. Here I have the examples of the components, which are the RTSP component and HLS component. In case of RTSP, what you can do with it is to receive some media from an IP camera. So let's say you have a network of surveillance cameras. You can add the RTSP source, and using the call to add component function, you have to know the URI of the RTSP stream, and then Jellyfish can use the stream, for instance, to forward it to other types of peers or components. And there we have the HLS component, which can consume other types of streams in Jellyfish and create a single stream where the audio from all of the other streams is mixed into one, and the video is composed onto a grid in a single frame. And then it is served via HTTP. This is how you do it in code. You can then use the HLS URL in your favorite HLS player for instance, the very popular HLS.js library for browsers to play the stream. This is the first use case, which is going to be WebRTC to HLS. So imagine the video conferencing solution. You have your meeting, which is represented by the room and Jellyfish nomenclature. You have your peers, so participants in your meeting, which are represented by the WebRTC peers. And then all of the peers can see, one peer can see every one of the other peers. So everyone sees everyone, basically. And then you can add the HLS component, which is at the bottom, to compose all of the streams from the other peers into one HLS stream, which is then served via HTTP. And I have a quick demo here. So in Membrane, we use this app that we called Membrane Video Room to basically do the internal meetings, which is the app is a simple clone of something like Google Meet. Let me just run it locally real quick. This is how it looks. I can add 2 participants to a room. As you can see, this is a simple video conferencing solution. It's obviously based on Jellyfish, so I can use the Jellyfish APIs to, for instance, and let me show you the slide, to, for instance, add an HLS component manually. And this is the code that we can use to do so. So we have to install the Jellyfish Server SDK. Obviously, this is Elixir. We can create the client struct, which aggregates information necessary to make the requests, which is address in cases, localhost, and some API token. Then, because we know that there's only one room on this Jellyfish instance, we can use the getAll call to list the rooms and somehow obtain the ID of the room. Then we use the add component function that we have seen before with the client, the room ID, and the HLS component to add the component. And I have exactly that here. Let me show you. This is the same script that I was talking about, except for some differences in the API token. And I'm going to call it with Elixir. And I have this URL, which I'm going to copy. And then I can use some example HLS player. In this case, this is HLS.js. To use the URL to play the stream back. As you can see, it is composed onto a grid. I can add, for instance, a screen sharing to the meeting. And you will see that in a moment, the screen share will appear on a grid. Here it is. Obviously, the way it works and how the grid behaves can be configured, but generally, this is how it works. Let's get back to the slides. So this is the other use case that we can achieve with Jellyfish, which is RTSP to HLS. We simply replace the WebRTC peers with RTSP components. So let's imagine you have a network of surveillance cameras, and you want to compose images from all of the cameras onto a single frame and show it in the browser, very similar to what we've done just before, but instead of my face, you would see the feed from your IP cameras. And this is all of the code necessary to create this exact scenario. So we create a room, we add the HLS component, which we've seen in the demo before, and for each of your cameras, we add the RTSP component. And that's basically it. This is everything you need except for the client struct that you've seen before. Okay, now we've seen some scenarios that you can achieve with Jellyfish, so let's get a bit more into the internals and how it works. We use this simple REST API for creating, managing, and deleting the rooms, peers, and components. And then we use the WebSocket API with protocol buffers for the notification API. So Jellyfish can produce some types of notifications, for instance, that the room has crashed or that the peer was connected. There's a difference between adding a peer and then connecting the peer via the signaling channel. And you also can receive some types of metrics, for instance, resource usage. And then there's the signaling channel, which is established between Jellyfish and your client, which is necessary for the WebRTC. And you don't really have to care about what's going on in this signaling channel, and it is abstracted from the user mostly. And then there's the actual media exchange, which is usually over RTP, which is made by RTP over UDP for WebRTC and RTSP, and HTTP for HLS. Obviously, as you've seen, doing all of the requests by hand would be quite tedious, so we've created SDKs in different languages. In case of the server SDK, so the creating rooms components and identifications, there's SDKs in Elixir, obviously, and in Python. And then for the front end, there's SDKs from TypeScript, React, React Native, iOS, Android, all of the jazz. Okay, so even with the SDKs, the development would be quite tedious. So we've also made a simple web app that can do everything that the SDKs can do, but in a nice web form that is hosted statically somewhere on GitHub pages, I think. The other thing somehow connected to the APIs is load balancing. We wanted to create Jellyfish very easily, horizontally scalable, which we achieved partially. This is basically the first step in this direction. You can create Jellyfish clusters, and then if you create an add room call to one of the instances in a cluster, the instance will ask all the other instances for the resource usage, and the resource usage might be, for instance, a number of tracks, multimedia tracks that are being handled by this particular instance. Then it will choose the one that is least used, basically, and create the room there, which is, all of this is abstracted from the user. And we use Erlang distribution for this with Flip Cluster, which is explained in detail by Arthur in the previous talk. And so I'm not going too deep into this. And that's basically how it works. We've also working on things like distributed rooms, so rooms that can span multiple Jellyfish instances, but this is quite a bit more complex, and it would require media exchange between different instances of Jellyfish. So this is in works at the moment. Before we get into the multimedia part of things, let me give you a little intro to Membrane Framework. I'm wondering how many of you have heard of Membrane? And how many have used Membrane? More or less what I expected. And so I'm going to give you a little intro to Membrane. Membrane is an Elixir framework that allows you to create multimedia pipelines. And basically, it's an abstraction of our Elixir processes that allows you to connect these elements and basically add some functionalities that are required for media processing. So these are the three types of elements that are available in Membrane. These are the sources which produce media or anything, basically. You are not constrained to using it for media. Then there's filters, which filter, and they take some media, do something with it, and produce some media. And there's sinks, which only consume. In a real-life scenario, this would look something like this. You have your file source, which reads something like an MP3 file, so audio file. Then you have a decoder, because the audio is obviously encoded. Then you have a converter, which converts the audio to a format that is playable by your speakers. And there's the player sync that plays the audio from your laptop, for instance. And this is a very simple example, and this is how the code would look for it. So you have your use membrane pipeline call, then you create this spec, which is basically exactly what is shown on the image. You have your file, then decoder, then converter, and then you pass the spec into the return value of the function, and that's all. This is everything that you need to create this pipeline. Obviously, the pipeline can be a bit more complex. Your pipelines can branch out. You can dynamically add and remove elements from the pipelines. Membrane also implements some features like back pressure mechanism. In case one of your elements is working much slower than others, the queue of buffers can grow infinitely. So there's the mechanism that the slowest elements has to explicitly request more buffers in order to not overflow the queue. Obviously, it allows you to reuse the existing components, and there's already plenty of components implemented by us, basically. Like encoders, decoders, MOOC source, stuff for reading, sending the data via network, and much more. This is a screenshot from a tool that we use to visualize the pipeline. It is called Membrane Kino. It is a plugin for Livebook. You can find it on our GitHub. It's very useful. And this is pipeline that is underneath one of the rooms on the Jellyfish instance. So the blue rectangles are membrane filters. In this case, all of them are T elements, which basically multiplex the media. So they take something on the input and produce the exact same thing on every one of the outputs. The green elements are membrane bins, which are basically containers for other elements. If this was interactive, we could expand the element to see what's inside, and we're going to do that exactly in a moment. And each of the membrane bins, in this case, represent one component. This is the RTSP component, and we know that even without looking what's inside, because it only produces media. And the media is then forwarded to all of the other elements. In this case, WebRTC peers and HLS component. And this is the HLS component. It only consumes media and then creates the live stream that you've seen in the demo. And also there's the WebRTC peer, which consumes media from other components and peers, and also creates media, which are usually, for instance, a camera feed from your participant in your video conferencing meeting, or his audio, or his screen sharing, or multiple video tracks with different bit rates and resolutions to better match the sent media to the network conditions. And now we're going to take a look how the LJS component actually looks. And this is the screenshot. As you can see, it really is a pipeline. In this case, there's only one video and one audio input, so the mixing part doesn't really do anything. And it's kind of hard to see what's going on the screenshot, so I created this nice diagram that shows you how it actually works. So let's say we have WebRTC peer and RTSP component in our Jellyfish room. They use RTP protocol. So in order to use the media, we have to somehow take the payload out of the RTP protocol. And this is done by the RTPD payloader elements. All of the rectangles in this example are membrane elements. Then we have to decode the media in order to mix them together. So we use VP8 and H.264 decoder. These are different types of video codecs, basically. And we use Opus decoder and AAC decoder. These are audio codecs to decode the audio. Then all of the video is fed into the video compositor, which composes the video onto one frame like you've seen on the demo. And all of the audio is mixed into a single stream. Then it has to be once again encoded. And then the CMAF payloader and Maxor element can take care of doing the actual MP4 segmented and then send it via HTTP. All right. So that was the Jellyfish. I hope now you understand some of the basics of used media streaming protocols and also know how to use Jellyfish in some basic scenarios. If you're interested in multimedia and Elixir, please check out obviously Membrane. If you want to know a bit more about Membrane, ask these two guys in the front row. They know much more about Membrane than I do. And also recently there was a 1.0 release of Membrane, so the API might be stable now. Also there's the Elixir WebRTC project, which I work on with my one colleague, Michał Śledź. And we're making a pure Elixir, no membrane implementation of WebRTC. If you're interested why, I'll be delighted to tell you more about it later. And also there's Membrane Cloud, which is a SaaS service. If you don't want to bother with your own infrastructure and use the Jellyfish, you can keep an eye on Membrane's Twitter and to see what's going to happen with this project. All right, thank you for listening.
Questions? Oh. By the way, if you're on stream, you can write on Wova app and I can read it out.
First of all, great job on what you did. And Are you thinking about implementing other protocols?
Yes, we are doing that exactly right now. Maybe exactly in this moment, actually. We're working on, some, for instance, voice over IP support for calling into your WebRTC meetings. Also, there's plan for simply not protocols, but elements that can, for instance, read media from file, so maybe an MP4 file, and then feed it into the instance of Jellyfish. So yes, we created it so it's very extensible, and we can very easily add other types of protocols and types of components, like I just mentioned.
Great, thanks.
Thank you.
Any other questions?
Here's one.
Does it support recording?
Sorry?
Does it support recording?
Work on recording is actually probably also done at this very moment. So yes, we're going to support recording the HLS feed, so decomposed image, and also we'll probably add support for dumping the RTP packets, so we can do something with it later on, some post-processing.
Nice job.
Thank you.
Thank you for sharing this knowledge with us. I have a situation where I have some pre-recorded videos, and on this device I'm producing videos for another dumb device like Chromecasts, and I need to combine some videos and put some dynamic information on these videos. Do you think I can use Membrane for that? There is a way to do something like a layout or layer over the videos?
Yes, you can use not Jellyfish, but Membrane. We have something called the Membrane Video Compositor plugin. I think it's still under development, but it supports things like composing the videos, overlaying with some text, using some custom shaders, and you can create your own pipelines that support this video composition thing.
Basically, it's based on the WGPU, so everything you can do on the GPU, you can,
Yeah, so Membrane Video Compositor is based, actually it's right now written in Rust, and it's kind of communicating with the membrane element that will plug into the membrane pipelines, but basically everything you can do on the GPU, you can do there. So, yeah.
I would like to know how, is Jellyfish supporting all the codecs available on the marketplace?
I don't think anything supports all the codecs available on the market. But it does support, currently for WebRTC we support H.264 and VP8 and Opus for audio. And also there's support for H.264 in RTSP and AAC in RTCP, I believe. And HLS can be only uses AAC and H.264. But we can add more. And there's already plenty of membrane elements that they can take care of decoding and encoding. So this is a matter of some work.
Thanks for the presentation. It was very informative. Are there any built-in tools to actually track fluctuations in the network or any other concerns that happen when you typically have videos? Video pauses at time, audio echoing and other things around?
I mentioned the metrics, so you can use the notification API to receive some metrics about, I'm not sure if it's exactly network usage, but for network usage, when developing WebRTC application, Chrome supports something which is called WebRTC internals. So in your browser, you can see all the statistics about bit rates and packet loss and stuff like this. But I don't think we do something more advanced than this in that case.
One more question. Did you run some benchmarking or something to compare with other solutions out in the market?
We did. Obviously, it's Elixir, so it's not going to be as fast as Go or C, but it was doing quite fine. I don't have exact numbers from the top of my head, but I think for HLS we were able, without any CDN support, a few thousand concurrent streams. So this is probably as far as you will go when using Jellyfish, for instance, in your for your company's meeting, let's say. But yes, I don't have exact numbers at the moment.